Section 7.8, improper integrals. So up until now we have found definite integrals where they were defined on a finite interval AB, and we also kind of assumed that f does not have an infinite discontinuity, means f does not have a vertical asymptote in that interval. In this section we will be covering two new kinds of integrals. These are kind of definite integrals, but they are over intervals which have vertical asymptotes, or intervals which are infinite. So infinite intervals look like something like a to infinity, or minus b to minus infinity to b, or minus infinity to infinity. And so the integrals of this type, these are called improper integrals of type 1 in your book, and means intervals over the integrals over infinite intervals. Now we saw these three examples in class, that if we have a function 1 over x, now note here the function 1 over x, the graph will look like a piece here and a piece over here. So we are talking about integral from 1 to t. So 1 is somewhere, let's say 1 is here, then eventually we are trying to take the limit of the integral. So we are actually looking at something like this. So in other words, if we are looking at integral from 1 to infinity, then we say from up to infinity. So in next example, we had 1 over x squared dx, which is also has a similar kind of graph, but this time the graphs are both above the x-axis. So again we are talking from 1 to infinity. So we are talking about this region. So that is what our integral from 1 to infinity 1 over x squared dx will look like. And in the last case, we have 1 over x to the 2/3. So again, the function x to the 2/3 will have one piece over here and one piece in the third quadrant, but it has a vertical asymptote at 0. But we are talking about integral from 1 to infinity. So this is how it looks like, and we saw that two of these diverge or do not have limit, and one converges or has a definite limit, and the one which we had limit was 1 over in x square. So the integral, which looks like this, is finite and has a limit. The other two didn't. So what was the common things between the ones which diverged and the one which converged? So we find out that if a function looks like, or the integrand looks like this, 1 over x raised to some power, then if p, the power, is less than or equal to 1, then the integral will diverge, and if it is greater than 1, then it will converge. And this is a kind of a proof that I showed you, and we did it in class as well. Okay, so now going back, so now we have seen some examples. So notice here, these are the proper definitions of the improper integrals. And what we do, if we have an integral of this type, a to infinity f of x dx, we will write it as limit t goes to infinity a to t f of x dx. And this is the kind of thing that we actually did in these problems up there. But now instead of plugging in numbers, we will actually find the limit using our methods learned from Calc 1. And similarly for this type of integral, because the infinity is at the bottom in the lower limit of the integral, so that will be replaced by t, and then we say limit t goes to minus infinity, and then we integrate the integral. So now there can be a case where at both places you have the infinite limit. So you have negative infinity at the bottom and infinity at the top. Then what you do in that case, you split the integral. Where do you split? That is your choice. You can pick any number, any real number, a, and write the integral from negative infinity to a to plus a to infinity. And again, remember, we can do that by the properties of definite integrals. So let me show you how actually we are supposed to solve an integral like this. Up there, remember, we solved it by plugging in values for x, for t, and then integrating. But now this is the proper way that you will be using in this section. So you will write the integral as a limit as explained in the definition. Then you will integrate this or solve this integral. So in this case it is ln of x, limits from 1 to t, and then limit as t goes to infinity, ln of t minus ln of 1, but ln of 1 is 0, so we are left with ln of t, and outside limit t goes to infinity. And again from Calc 1, recall that this is infinity. And again, why is that infinity? Because if you look at the graph of the logarithmic function, so if this goes like this, where this is 1, so as x is going to infinity, you can see that the function is going to infinity. When you look at x square, 1 over x square, so we have to integrate from 1 to infinity, so we write it as limit t goes to infinity 1 to t 1 over x square dx. Now the integral of 1 over x square is negative x to the negative 1. So plugging in the integral limits, one upper and lower limits, so then we have negative 1 over t plus 1, and again from your limits from Calc 1, notice that limit of 1 over x as x goes to infinity is 0. So applying that on the first piece here, we get 0 plus 1. So the final answer is the limit is 1, and that's what we found when we were doing it by giving it values. Same thing now here. We have 1 over x to the 2/3. Write it as a limit like this. Integrate. We end up getting function 3 times cube root of x. Apply the upper and the lower limit. We end up getting this, and now when you apply the limit of cube root of t as t goes to infinity will be infinity, and minus 1, so that's infinity. Okay, now let's look at a couple of little bit more involved examples. So here the first one is 0 to infinity e to the minus 2x dx. So the first thing you will do is write it as a limit t goes to infinity 0 to t e to the minus 2x dx. And now it's your choice if you want to continue like this, but I would recommend that you first find the integral, because in some cases you will have to use the integration by parts, or sometimes even maybe partial fraction, sometimes some substitution. So keeping all things together becomes kind of cumbersome. So we will first integrate the function, and then we can apply the upper and lower limits of integration, and then take the limit as t goes to infinity. So step by step. So in order to do this, you can say let u equals to minus 2x, which will give you that du equals minus 2 dx, and then you can find dx from here. So this integral will become integral e to the u and minus 1/2 du. So that minus 1/2 integral of eu du, which is minus 1/2 e to the u, or minus 1/2 e to the minus 2x. Now note here I am not putting a plus c here because I know it's a definite integral. And now we have to take the limit. So limit as t goes to infinity of negative 1/2 e to the minus 2x, applying the upper and the lower limit. So this gives me minus 1/2 limit t goes to infinity of e to the minus 2t minus e to the 0. E to the 0 is 1. So we end up getting minus 1/2 limit e to the minus 2t, t goes to infinity, minus 1. Now this limit, again recall, this limit is 0. So that we end up getting the answer negative 1/2 times 0 minus 1, or 1/2. So this is a convergent integral, or the integral converges. Looking at this example, so first we write by as a limit as t goes to minus infinity in this case, and then we will put the t here, and negative 3x over 4 minus x squared dx. So again, using u substitution or using the trig substitution, x is equal to 2 sine theta, you can do it. I think with u substitution it's easy. So we will let u equals 4 minus x squared, then du will be equal to minus 2x dx, and you can figure out from here that dx is du over minus 2x. So we are only looking at this in piece now. Remember, we will apply the limits later. So this becomes x over u times du over minus 2x, which is going to be minus 1/2 integral of 1 over u du, which is negative 1/2 ln of absolute value of u, or negative 1/2 ln of absolute value of 4 minus x squared. Now we will apply limit. So limit as t goes to infinity of negative 1/2 ln of 4 minus x squared. Apply the limits from t to negative 3. So this will be equal to limit as t goes to infinity minus 1/2 times ln of absolute value of, now this will be 4 minus 9, but notice here that's why absolute is important, because we are going to get a negative 5 inside the logarithm, and then that logarithm of negative numbers do not exist, but the absolute value will make it positive. And then minus ln of 4 minus t squared. But notice here, if we get negative 1/2 ln of 5 plus 1/2 limit t goes to infinity ln of absolute value of 4 minus t square. Now notice that as t goes to infinity, this quantity will go to infinity, and ln of goes to infinity, so that this is infinity. So this diverges. So this is how we find these or solve these improper integrals when we have infinite intervals. Now the next thing we will look at is the other type of improper integrals.